Thanks again for the invitation. A lot of thanks to the organizers for having me here. And today I'm going to talk about, oh my God, certain quantum algorithms for computing representation theoretic multiplicities. This is joint work with Wojciech Havlicek from IBM. It's been published in PRL last year. And yeah, I hope you enjoy it. So the motivation for this work was the following. Like there's this, of course, very big question of what are quantum computers good at. I mean, and it's arguable that we don't have a complete answer to this question. And it's kind of one of the main things one can do is just try to look at the successful quantum algorithms that have certain, like at least speedups with the best known classical algorithms, and try to understand what's behind the speedup. So some of these speedups that we know seem to be rooted in the fact that quantum computers can implement Fourier transform very efficiently. For example, the quantum Fourier transform over the cyclic group can be implemented in depth polylogarithmic in the order of the group, while the classical implementations are linear, at least linear in the order of the group. And okay, and then this is the motivation of the work. Like, this is not the end of the story. There are also efficient quantum Fourier transforms over other groups beyond abelian groups, for example, non-abelian groups, like finite non-abelian groups, like the symmetric group, and so on, that are also efficient they're also efficient in log of the order of the group, and the best classical transforms are also kind of not efficient in log order of the group, yet we haven't found good applications for these transforms. And the main kind of way of thinking for applying this has been mostly trying to solve non-abelian HSP, which is a direct generalization of abelian HSP, which was the kind of the application of abelian QFTs. But it has remained an open problem for more than 20 years, and it's a very hard problem. So what we tried to do in this work was try to leave HSP aside and try to see what other things we can do with the ability to query the Fourier spectrum of quantum states. Let's say the non-abelian quantum Fourier spectrum. And we find that something that it's like very naturally allows you to do is compute multiplicity coefficients of irreducible representations in certain group representations. And as a case of irrep multiplicities is the computation of Kronecker coefficients, which are the irreps appearing in the tensor of two other irreps of the symmetric group. And the algorithm we found is efficient in certain regimes where no classical algorithms were at the time of putting the paper out. Then the math community was interested and took a look at it, and there are also classical algorithms in these same regimes. Yet there are still large polynomial gaps. For example, for an arbitrary parameter k, the classical dequantization, let's say, I mean, I call it dequantization because both are polynomial in the same regime, but the classical is n to the k square, and so let's say k is order 1, but the classical is still n to the k square, and our quantum algorithm is n to the k. So there's a still very large polynomial gap. And this is for a given subset of Kroneckers that are called diagonal Kroneckers, but more generally, there is still potential for superpolynomial gaps in other regimes. So to explain the problem, let's start with a little bit of recap of group theory and rep theory. So a group is a set G with an operation circ between like G times G. So it takes two elements of the groups and gives you a new element of the group. The properties are it has an identity and every element has an inverse, such that if I do element and inverse, I get the identity. A representation or a group representation more strictly, and in fact I'm going to only do unitary group representations, it's just a map from an arbitrary group G. So, and it's called a representation for G on H, which is a vector space, is a map R from G to the unit that is on H. So both G and UH are groups, and this is a map between groups. And the only thing that you ask this map to satisfy is that this group homomorphism property that is just saying that it preserves the group structure. If you compose group elements and represent them, or like represent them and then compose the matrices, it's the same thing. And this doesn't mean that the kind of the image of R is isomorphic to G. Really, I mean, you can really have like a big kernel of this map. In fact, like you can map G to the identity matrix, and that's a representation. Then everything is a kernel, right? So it's not that the image of G is going to be isomorphic to G. The image of R is going to be isomorphic to G, but in any case, it's satisfying the composition of elements. And this allows groups to act on vector spaces, and we're going to call those vector spaces, like in general, d-dimensional complex vector spaces, group modules. Fundamental result in rep theory is that all of this, any group module over the complex numbers for a compact group. So all of this is assumed in my lecture. I'm going to just use finite groups, so don't worry. There's always a choice of basis for the module such that the group action is maximally block diagonalized. So in certain bases, I choose for this guy, which is kind of basically this one. It looks like blocks where like a certain irreducible representation is repeated a certain number of times. So if I choose this given basis, so I mean, and for the basis, I can use a label for the irrep, a label for the irreducible representation, and a label for the copy. And then in this basis, if I rotate any RG, it looks like certain blocks that are repeated certain times. And these are unitary blocks too, but are smaller, of course. Yes, I think this is the definitions we need to introduce. As I said, like we were going to use d gamma for the dimension. The important thing is that for certain reasons, this transform, this basis is called Fourier basis. Again, it's maximally block diagonalized and not block diagonalized just because the group is non-abelian, right? So in principle, we have a set of order of G unitary matrices, RG, for every G in G. And we want to diagonalize this all together, but they are non-commuting, so this is kind of a hopeless problem. But except the group is abelian, but still we can find a basis where they are as diagonal as possible, and that's what we call a Fourier basis. And the transform U that is taking me there is called the Fourier transform. I'm going to use this notation for a given arbitrary group representation R. I'm going to call it R quantum Fourier transform, okay? And these things, all of these things that are kind of each block where like little blocks are repeated same time, so all of the collection of all irreps of the same time is called isotypic component of type lambda in H. You're going to use pi gamma, and this should be a gamma, I'm sorry. I'm going to use gamma for irreps of G. So this is gamma, type gamma in H, and pi gamma, the projector into that subspace. Some comment is that the set of multiplicities for all gamma in H or in R uniquely determines the rep, okay? Up to homomorphism, up to an isomorphism. This is similar to how the multiplicity MP of each prime P in an integer n uniquely determines it under this equation, right? 2 to the number of times n2 appears in n, 3 to the number of times 3 appears in n, and so on. So in a sense, if someone hands you a representation, you can ask the question, what's the set of multiplicities? And from the set of multiplicities, you can reconstruct the representation. And in this paper, we will deal with the computation of not the multiplicities of primes, but the multiplicities of irreps irreducible, these ones, or these ones. As a grounding example, maybe for physics people, recall that if you tensor two SU2 irreps that are labeled by spins, spin 1 and spin 2, you're going to produce new irreps that are spin S, in this range of possible spins, each with multiplicity 1, right? And the Fourier basis mapping, the tensor basis, so the basis S1, M1, S2, M2 for M1 and M2 projections of spin in the, for example, Z direction. There's another basis called the coupled basis that is an S and M, and there are kind of Clebsch-Gordon coefficients that map between one and the other one, and this transform is called the Clebsch-Gordon transform, but it, in my kind of notation, is just a Fourier transform. It's a Fourier transform that block diagonalizes the tensor rep of two spins. Okay? And we're gonna compute multiplicity, so if we compute multiplicity for this problem, it's kind of a trivial case, right? Like, nothing's gonna happen. If you then go to like SUD E-reps, it starts getting more interesting. The multiplicities are little with coefficients. And we're gonna do the same. We're gonna tensor two symmetric group E-reps, and the multiplicities are gonna be Kronecker coefficients. Okay, so let me explain what, so many times we don't really need a full coherent Fourier transform over an arbitrary rep. It's enough to implement this measurement that I talked about. It's a projective measurement into only the isotypics, right? This is called weak Fourier sampling. And of course you can do it just, we have a drawing in the, look at the A case. Of course you can do it if you have your R, representation R for G on H. And of course you can apply the RQFT. This is gonna give you, again, if you want a gamma label, kind of B gamma, and a multiplicity register, you can just like apply the QFT and measure this label. This is going to implement this weak Fourier sampling. But as I'm saying, this is not necessary in principle. You can replace all of this by the following algorithm, which is called generalized phase estimation, introduced by Adam Harrow in 2005. And as I'm saying, it implements weak Fourier sampling without the RQFT using a left regular ancilla. So you have now a control register here, control R operation, and a regular QFT. So let's see how he does it. You have a left regular representation on top. A left regular representation is a representation for a group on itself, basically. So the vector space it's acting on, it's the linear combination of group elements. You apply a QFT, an inverse QFT on a trivial E-rep to produce a superposition over the group elements. So this is your state. Then you apply a control R. This is where the actual R, arbitrary R is acting. And as long as you can implement this control, so this is a unitary operation that would kind of look like get bra G tensor RG on the target. And then you apply the like forward QFT over the left regular representation, which typically is easier to build than just this one for arbitrary representations, because the left regular representation is very structured. And then you measure the E-rep label, okay? And just note that if we send a state that's proportional to the identity in the group module H, we will get outcome gamma after the implementing measurement pi gamma with the probability trace of pi gamma, which is the dimension of pi gamma, which is d gamma times m gamma. D gamma is the dimension of the E-reps, and m gamma is the number of times they appear. So we already see what's the strategy we're going to use. We're going to try to do something like this, and then try to compute m gamma from estimating the probabilities. Okay, we will sample many times. We will initialize identities. We will sample many times, compute estimators, and then kind of divide by d gamma. And that's kind of the end of the game, plus minus some details. Okay. So now I'm gonna try to argue that. I mean, I argued that previously, but let's argue a little bit more why that quantum computers are great at Fourier transforms. And as I was saying, one of the instances where we kind of know they're really good is at the quantum Fourier transform. That is the Fourier transform over the left regular representation of the cyclic group of integers under addition module n. As I already mentioned in introduction, that the cost of DFT or FFT is poly n, and the cost of QFT is only log n. But of course, DFT and FFT produce the whole kind of Fourier spectrum for you. Instead of quantum computer, will only kind of produce a state, and then you're going to have to sample. So the obvious challenge is to use the samples in a non-trivial way, and non-trivial ways of using this quantum speedup in rotating the computational basis, or if you want the group basis of integers module addition n into a basis where the cyclic groups acts maximally diagonally, which is in this fact because it's abelian is fully diagonally, has been found and led to some of the most successful quantum algorithms known to date, period finding, factoring, abelian HSP. Similarly, we've known QFTs for the symmetric group, but applications have failed so far, most applications. So this is our kind of general algorithm for an arbitrary group over which we will assume we have an efficient QFT over the left regular representation, and some arbitrary rep over which we don't have a QFT, but we want to use GPE algorithm. So again, like a general form of the Fourier basis and like how the group elements, represented group elements look in the Fourier basis, isotypics, and these projectors that we want. Our algorithm looks like initialize the maximal mixed state over H, as I was already kind of pointing to. Then implement weak Fourier sampling, and you'll obtain out and gamma with this kind of probability that's proportional to the multiplicities. Repeat many times. Each time you will get a single shot estimator for p hat. Then you basically compute this quotient of d gamma over dh. You should be able to compute d gamma and dh efficiently. This is non-trivial, but in the case we're going to instantiate, in principle, you can do it. And therefore, like, you can work out. So basically, the sampling cost will depend on the dimension of the ambient kind of rep h over the dimension of the rep squared, because you're sampling. I mean, you can probably make this better if you do amplitude amplification. Like, you can probably remove this thing, but we didn't care about that here. This looks very simple, but the art is in finding relevant multiplicities and efficient ways to initialize maximal mixed states over group representations and implementing weak Fourier sampling. So the general algorithm looks like this. So we know that was general. Whenever you can do all of, like, again, whenever you can do these things that I'm saying here, initialize rho h, implements that with Fourier sampling and so on, you can get gamma by sampling, m gamma by sampling. Now we're gonna look at the still very general, but a little bit more special set of representations, which are restricted representations from an ambient group A to a subgroup G. So let's say you have an E-rep alpha of an ambient group A. We call it W alpha. If we now look at a subgroup, this will be also a representation for the subgroup, and in principle not irreducible. So if you look at how an alpha rep of A looks as a rep of G, it's gonna decompose into multiplicities, and we're gonna call the multiplicities that appear m gamma in alpha, basically. And again, we apply the previous algorithm to this case. Recall that it amounts to preparing maximal mixed state and Fourier sampling over the G-rep. And here we do the assumption that we have efficient quantum Fourier transforms over ambient and subgroup, and control operations between the left regular reps of both. So the two parts is state initialization. So how do we initialize the maximal mixed state over the restricted rep? Well, we just need to initialize it over basically the alpha E-rep. So one thing we can do is initialize a register with the whole kind of group algebra of A, a left regular register for A. A and G are finite groups, right? So you need log order of A qubits. And what you do is you basically, since you have efficient AQFT, you can apply it in reverse on the trivial. No, you can apply it in reverse on the alpha E-rep and set the copy index to anything. So you apply it you put a maximally mixed state over the alpha E-rep and a projector here, and initialize like any copy of it. You have the alpha copies of it in the regular rep, so you should just choose anyone. Here I choose the first one. You apply QFT, AQFT in reverse, so you're preparing the basically maximal mixed state over this W alpha. That's the first step. The second step, you apply Fourier sampling over the G rep. So you apply GPE essentially. So here I'm drawing it. As I was saying, you initialize over alpha and a kind of a maximal mixed state in the kind of alpha register and just pick a copy, inverse AQFT. And here you apply this GPE algorithm that I was describing previously. This will produce the samples that you want with the given probability that is proportional to the multiplicities. So all you need to, again, I assume that this cost of, let's say, like time cost of AQFT, of GQFT, and the control operation, all of this I collect in something that's called D, and I'm going to use D for literally the cost of a single run of this algorithm, and then I need to repeat this D alpha over D gamma squared times. I think the summary is again, you initialize a projector onto an irrep of an ambient group, then implement projective measurements onto irreps alpha of an ambient group and gamma of the subgroup. And the probability will be proportional to the multiplicity of gamma in the restriction. Let's move on. So there really are there instances of A and G meeting these requirements where like QFTs are available and you have the controlled action and also computing the multiplicities, someone cares for them. And this is kind of the application, Kronecker coefficients. The ambient group is a tensor of 2 copies of the symmetric group, and the subgroup is the diagonal, basically the diagonal pairs inside of A, which is isomorphic to Sn, of course. And control action between because you have the ambient are 2 CSN registers, and the subgroup is also a SN register, so essentially the control action can be implemented as a reversible circuit in depth order n squared. This is a claim, but like it's not hard to see how you do it. The actual bottleneck is the SNQFT, which is polynomial in order 4 in n. Here are some papers that discuss SNQFT. There's also an in progress paper by Brinsma, Grinko, and Ossos that seems to have a n to the 3.5 complexity, which is very interesting. But let's assume it's n to the 4 for now. And as I was saying, like if we take the A, remember A is 2 copies of Sn, so we can really take an A irrep to be mu and nu irreps with mu and nu partitions of n. And this will give us kind of the rule for the Kronecker coefficients. So this is the A irrep. And then if we think of this as a G irrep, it will break into Kronecker coefficients for each lambda. That's the multiplicity of lambda in A in the restriction. So just doing some numbers, I was saying that the complexity. So look, basically the sampling cost is D alpha over D gamma. Alpha is D mu D nu, and gamma is D gamma. So we get something like this, n to the 4 times all of this. Here's a drawing. How I'm doing with time? 3 minutes? Perfect, yeah. Yes, I think we can do it. It was a little fast, but so the drawing is showing you the actual circuit, right? Like you have a control that is as I was saying, you have a target where you have the H that you're gonna use for looking irreps in H. In this case, you took the group algebra of A and you restricted to G. So in this case, it were 2 CSN registers, and you're applying GPE on that. So to apply GPE, you initialize another CSN register. So you in total have 3 symmetric group registers, regular registers. You apply inverse SNQFT, you control, and then you apply forward SNQFT. And the claim is that you're gonna sample with probability proportional to Kronecker's if you initialize projectors into maximal mixed states of isotypic lambda and mu in the target, okay? Come on. And of course, in general, like this kind of proportional. This sampling cost is not efficient because again you have irrep, dimension of irrep over dimension of irrep. In principle, SN irreps can be exponential size, so like you have 2 over 1. It can be exponential, okay? But in the case that if you take diagonal Kroneckers, which are the case where 2 of the 3 partitions are the same, you get this cancellation, okay? For example, if you take like mu and lambda, the mu's go away and you just get proportional to lambda, so you can get efficient algorithm whenever the dimension of the symmetric group irrep is polynomial. So just you need to ask when is this polynomial, and you just draw any partition lambda and you call k the number of boxes below the first row, and the dimension of that guy is n to the k. So whenever you have order 1, whenever you have k boxes below the first row, our algorithm will compute diagonal Kroneckers for any mu, really any mu. The only condition is on lambda, in a time efficient, okay, polynomial time, and the polynomial is n to the basically 2k plus 4. For reference, there were no efficient classical algorithms for doing this. The best kind of known things were basically by Christian Del Dorian and Walter, based on counting lattice points in polytopes, and the Kroneckers were computed in time exponential in the max length of all of them. So like really, like for example, the mu length would appear here. In our case, it doesn't. Yet, oh, yes, I went too far. So, and Greta Panova studied the problem and found a classical algorithm, as I said in the beginning, but it's n to the k squared. So yes, even at k equals 3, you have a quantum n to the 10 versus n to the 37 classical. Even if it's optimal, not optimal, the classical one, this is very large separation. And also I want to mention that there's also the possibility that this quotient is polynomial with all 3 of them being super polynomial, and in that case there's no kind of classical algorithm possible, but the quantum algorithm would directly be efficient, okay? So we're looking for this regime. These are other coefficients that you can compute, like similar by taking other ambient groups and other subgroups, Koskov-Littlewood platisms, but we don't have time to explore them now, and with that we can discuss what we've done. We gave a quantum algorithm that can compute multiplicity coefficients for arbitrary group representations, provided that we got efficient QFT over the left regular representation of the group, and we can initialize maximum mixed state onto the representation, and we can implement the control group action. An instance of all of this is when you have you essentially have an ambient group, and you have also QFT over the ambient group over the left regular representation, and you're going to consider the rep of G to be the restriction of an irrep of A. You exemplified Kroneckers are a case of this, Koskov-Littlewood and platism are also a case of this restricted algorithm. And the complexity of the restriction algorithm will be kind of the irrep of A over the irrep of G squared. As I said, all of this is okay. We illustrated the potential for diagonal Kroneckers. There's a n to the k versus n to the k squared separation. So there's known classical algorithms. And besides this work, this is a message, is Euler representation theory can provide an interesting framework to find very structured problems, albeit kind of arguable practical interest currently, but like still very structured, and where one can reason about them and find like speed ups over classical computation. With that, I finish the talk. Thanks.
Thank you for this talk. Are there any questions? I see. Jens, wait, let me get the microphone.
Great talk. Thanks a lot for this. I mean, can you make a connection to like learning theory in the sense of like, I mean, there's the hidden subgroup problem, and then there's the state hidden subgroup problem, where they're being presented states as the oracle axis. I mean, for your multiplicity coefficient computation, similar things should work, right? Where you get copies of a state, and then you kind of see the multiplicities that are
that's awesome. I mean, I didn't think about this. I think it's a good idea. Like in principle, I try to compute the multiplicities without anyone giving me anything. You know, I'm initializing them. You know, yeah. But it would be interesting to kind of say, what can you do with Fourier sampling when you have a resource, in the sense that someone's providing something for you, like you're saying, someone's providing states for you. Yeah, it's something one should look at. Thanks. Definitely. Thanks.
More questions? Yes.
Thank you. One question. So you need a quite singular set of circumstances for this to apply, right? On the one hand, you need to know a lot about the group because there's very non-trivial operations you need to be able to do. You need to, do the Fourier transform, measure the error spaces, even know the error labels and all that.
Yes.
On the other hand, at the same time, these simple, this way of combining them, Kronecker, Placism, they need to be difficult. So are there good candidates beyond the symmetric group that fall into this right niche of some things being easy?
Like symmetric group already gave 3 other coefficients that are also very interesting, right?
Right, but it's still for a symmetric group, right? So are there other groups for which you can do it? These different different ways of combining things in different groups you can work with, no? And for the different groups,
basically, I'm a little bit ignorant about other kind of groups with very good structure. I really kind of know the rep theory of the symmetric group, and that's why I use it here. I really don't know like other groups that have like such a very nice representation theory that can be used. But still, we frame it in general in case someone does.
Thank you.
Thanks. It's a good question.
More questions? I think I saw. Yes. I'll coming to you.
Maybe you can compute Clifford Clifford coefficients. We can talk about it.
Thanks for a nice talk. I have one question about this classical algorithm. Is it randomized? The classical algorithm that's
yes.
solved?
Yes.
So is it randomized or?
Yes, it's randomized. Yes.
So what if one just do
amplification
on the
sorry?
Top? What if one does amplitude amplification on the top of that? Then one would get similar complexity to yours, if I understand. Or
if I do amplitude amplification over my quantum algorithm
of theirs.
I would remove the square. It would be like n to the k plus 4 instead of n to the 2k plus 4. I think it's I haven't done it we didn't, but it's kind of clear that there's nothing stopping you from doing that.
Amplitude amplification of theirs gives basically what you have.
Sorry?
Doing amplitude amplification on the top of that classical algorithm gives the same performance as your algorithm.
That's it.
Or
no,
or maybe I got confused.
Like you need to remove a square on a square.
No.
I mean.
No. Sorry.
Exactly.
No, sorry.
It's a square on exponent.
Sorry.
Yeah. Nice.
All right. Any more questions? No. I have one selfish question.
Yeah.
So if I want to calculate these Kronecker coefficients classically on my laptop versus your quantum thing, how much do I fry my computer with that?
So there's a very simple way of doing it using characters, which simple but super not efficient. Right? Computing characters is also really hard. But I'm using characters. You can write code for it very fast. I mean, then if you want to do it classically, then I think the best bet is to use Christian, Dorian, and Walters if you're going for efficiency. Which again, it's exponential in the length of any of the partitions. So if all of them are scaling, the length, I mean the K, the thing that's the tail,
Under the Young diagram.
I mean, it's hopeless. It's exponential in that. So in our case, basically we're taking out two of the 3 partitions from the equation, basically. So you can have arbitrary tails for those and only basically look at having a small tail for one of them. So it's a kind of very niche kind of thing. But yeah, it's no one knows how to do it with the n to the k complexity classically today.
All right. With that, thank you so much again.
Thanks.